Okay, so that brings us on to chapter 2. This is about the boundedness of subsets of R to the D. This is a relatively straightforward concept about subsets of R to the D. And so, as with many of the other properties in this module, we're going to be looking at sets in d-dimensional space and trying to decide which of them have got a certain property and which of them haven't. So we're going to be looking at the nature of different sets in R to the D and trying to understand how we can distinguish between them, which ones share which properties, which sets are good sets for looking at continuous functions on, what can you say about continuous functions on certain kinds of set, and so on, that sort of thing. We're not going to, once you go into d-dimensional space, it's not going to be enough to just look at intervals. You're going to want to look at working on some rather more interesting domains than that. So that's the sort of thing we're going to be doing. In this chapter, we're starting off with a relatively easy concept, boundedness. Having said that, I find that more people get confused about boundedness than about the more complicated concepts that come later. And the reason for that is in the language. People get very confused about the words bounded and boundary, and also later when it comes to the word closed. And to make things worse, there are some differences between the way some of these terms are used in this module and the way they get used in G12 Vec if you're doing vector calculus. And that can't be helped. It's a part of the tradition in the way some of these terms are used. That means that you have to remember which module you're in if somebody uses one of these terms, and remember what that term meant in that module. They've all got precise definitions. So if you just think, I think I know what that means, but I can't remember the exact definition, then you could get into trouble. So you've got to understand the definition, and you've got to understand the examples. The examples will help you understand the definition, and the definition will help you understand the examples. And let's move on, and you'll see the sort of things that I mean. But it's very important that you do know this, because a lot of the other stuff in the module depends on the basic definitions. And if you don't know one definition, you won't understand the next definition, and you won't understand the examples. Now, we haven't defined closed yet, or open. We're about to define bounded. But one of the things you're expected to be able to do in this module, once we've done some examples, is that you're supposed to be able to look at various subsets of R to the D and work out for yourself which properties they've got and which properties they haven't got. So you're going to be expected to figure out whether or not a certain set in R to the D is bounded or isn't. I'll specify the subset by some definition or other. You have to figure out whether it's bounded or not, using the definition for this module, or sometimes you'll be allowed to write it down without justification, but that's only once you've got used to what it actually means. That's later. Same for things like closed sets and open sets, whose definitions are coming later. So here's this warning that unfortunately we can't do anything about. They use slightly different terminology in that module. Fortunately, bounded means the same thing. But unfortunately, there's a notion of a closed surface and a surface with boundary, and those concepts don't quite fit with the notion of closed set that we're using in this module, or the boundary of a set that we're using in this module. So things can go wrong. There is a connection between them, but it's a slightly subtle connection, and you can easily get confused. So make sure you know which one you're using in which module. So I want to move on and talk about different kinds of balls in R to the D, open balls and closed balls. Every ball will have a center and a radius, whether it's an open ball or a closed ball. And the difference between the closed ball and the open ball is what you do with the points that are exactly the distance from the center equal to the radius, whether they're included or excluded. In the closed ball, those points are included in the ball. In the open ball, they're excluded. So in the open ball, you take those points whose distance from the center, and the center is x, and the points that might be in it are y. So again, take careful note of this careful use of set notation. X is not varying here, x for the moment. X is the centre of the ball. And then you look at those points y whose distance from the centre x are less than r. So the y's that might be in the set are specified here. Y, all those y's in R to D might be in the set. Then you look at the conditions of y, and the actual condition is that the norm of y minus x should be less than r, and that helps you to determine which ones are in. And informally, and may formally later, you should think of that as a ball with radius r, but where you don't include the boundary. But we haven't defined boundary yet. But whatever boundary means, it's going to be you throw out the boundary. The boundary is excluded. Whereas in the closed ball, the boundary is included. But beware of the words bounded and boundary. Have a look at the module frequently asked questions document, because there have been a lot of problems in the past about this. And so I've answered some of the common questions in the frequently asked questions document, which you can get for the module web page. Special cases where you center the ball on the origin, you get what's called the open unit ball and the closed unit ball. These come in quite a lot later in analysis. We won't use them very often in this module, but they're like, well, the center is on the origin, they're radius 1, and you either exclude the boundary if it's the open ball, or you include the boundary if it's a closed ball. Let's just give you a couple of two-dimensional sketches, and you should think of these two-dimensional sketches as giving you a pretty good idea of what is going on in d dimensions. Two-dimensional sketches are quite useful. They often give you an idea what's going on, but they often don't count as a proof. So in 2 dimensions, so you take your point x and your radius r, and you draw a circle. Unfortunately, I get distortion on this screen, but I'll do the best I can. It's very difficult to draw a circle on this screen. I'm going to have to put up with drawing a circle on my screen, which will get slightly distorted on the screen you see. If I include the boundary, then I get the closed ball. And I have to remind myself, I use 2 different notations, one in this module and one in the next module. Yeah, I see. We're using BR of x in this module. If you do MTS, it's B of XR in G1 free MTS. So if I do accidentally switch notations, it'll be because I've got confused between the second and the third year module. Both notations are fine. And that's the boundaries included. In this case, it's pretty obvious what the boundary circle is. And then if you want the open ball, you just have to miss out the boundary, so I'll do the same thing but with a dashed boundary. So this is the open ball, centered on x, radius r. So again, it's a disk, but this time with the boundary circle excluded. So that's what happens in 2 dimensions. And in d dimensions, it's pretty much the same, except that in 3 dimensions, you're talking sort of spherical balls with spherical surfaces as the boundary, and then you move up into higher dimensions, and you're sort of the higher dimensional versions, which are sort of hyperellipsoids, but where all the semi-axes are the same, hyperballs, I suppose. Any questions about these so far? Do I need to go back to any of the pictures? Okay, let's move on. So it looks like I've already filled in these gaps. I've already done the closed ball and the open ball here. Here's a little exercise for you then. I'll just give you a couple of minutes to think about this, and then maybe you can tell me what you think the answer is. What are the open balls and the closed balls when d equals 1? So your task is to talk to each other, look at the definition, and bear in mind that as far as I'm concerned, that r to the d is just equal to r, and the norm of x minus y, okay, we don't need to underline them here. The norm of x minus y is then equal to just the modulus of x minus y for real numbers x and y. And so your task, sorry, that's r to the 1 equals r. This is when d equals 1. Your task then is to take the definition of the open ball and the closed ball and figure out what it means. So for x in R and a positive real number, and I'll notice if I say R greater than 0, I mean that R is a real number here. That shorthand, if I write r greater than 0, I mean that r is a real number and that r is greater than 0. Don't allow infinity. You have to figure out what is the ball in the real numbers, of course, centered on x, radius r. So why don't you talk amongst yourselves for a minute or two just to see if you can figure out exactly what that is, or about anything else if you like, and then I'll see who's come up with exactly what that set is in a couple of minutes. And meanwhile, I'll pause the recording. I was just asked about the spare handouts and so on. All handouts for this module are available on the web, and that includes the unannotated slides, and from chapter 1 that will include everything, including the bit that was missing, and the annotated slides as well. When I finish the lecture, the annotations go on the web as well. So everything is available. I hope that won't stop you from coming to lectures, because if you come here, you get a chance to ask me questions, and you also get a chance to see me waving my arms around, which is not available on the video. So let's see what people think. Let's see what people think. The answer is to this. Can anyone tell me what the open ball and the closed balls are? Well, what's the open ball for a start? Open ball centered on this real number, radius r. Anybody got a description for that? Possibly you don't want to tell me. I'm sure quite a lot of you know, but I know there's a lot of people in the room, so you might not be... you might not... I tell you what, if I promise not to pick on you, anybody willing to a show of hands of who thinks they know what this set is? And I promise not to pick on anyone. Okay, nobody's willing to own up to knowing what it is, but never mind, I'll tell you. But I don't believe you. I'm sure lots of you know what this set is. So BR of x is going to be those y in the real numbers here, because that's where we're working, so that, and as I said, norm comes out as modulus, so it's modulus of y minus x is smaller than r. If you think about it, that's those points that are strictly within R of x. That's those points strictly between x minus r and x plus r. So that y in R such that x minus r is less than y is less than x plus r. Which is just the open interval x minus r, x plus r, which is equal to, in our alternative notation, which I'll be coming back to in a minute, I think this machine doesn't like it when I do things too quickly, and you sometimes get these funny spikes coming in, which I just have to undo. So in our alternative notation, that's x minus r, x plus r. And we can sketch that on the real line. So here's your real line. Here's your point x. Here's, oh, sorry, no, don't need to underline it anymore. Here's x plus r and x minus r. And we get the open interval. And here's your set. Okay. And similarly, of course, the closed ball is equal to those y and r, which are strictly not strictly between. It's x minus r less than or equal to y is less than or equal to x, which gives you the closed interval. X plus r. As an exercise, you could sketch that. Right. So what we'll be moving on to next time then is a discussion of bounded sets and unbounded sets, and it'll all be defined in terms of these closed balls, but basically it means that they're not boundless. You can't sort of escape off to infinity.